Welcome back to this explainer brought to you by Forge College. So in our last session, we took this big bird's eye view of the overall SVM client architecture, right? Well, today we're grabbing our hard hats, maybe a strong cup of coffee, and zooming straight into the internal gears of the machine. Here's our blueprint for today's tour. We'll start with the blueprint itself, meet the components, check out the factory line, look at some real-world roles, and finally figure out how to spot bottlenecks. Let's dive in. Starting off with Part 1, the SVM client blueprint, and specifically the separation of concerns. The absolutely foundational principle of any modern blockchain node is this idea of separation of concerns. We literally never treat the node as a giant, tangled monolith. Why? Well, because if one single gear jams up, you definitely don't want the entire network catching fire. Instead, we want to treat the client as a series of specialized factory stations. Every station has one job and one job only, which makes scaling and especially debugging a total breeze. Moving right along to Part 2. Let's step onto the factory floor and actually meet these core components. All right, so everything starts right here at the intake funnel. We call this the networking and RPC layer. Think of it as the shipping and receiving dock. It handles secure peer discovery, network gossip, and all those user-facing JSON API requests. It's out there parsing raw network frames, slapping on rate limits so the factory doesn't completely flood, and safely forwarding the valid requests inside. Next up on the floor is the transaction pool, or as we all know it, the mempool. This is your staging queue for unconfirmed transactions. Honestly, the mempool is basically a chaotic waiting room. Think of it like the DMV on a Monday morning. Because it gets so incredibly crowded, it absolutely requires ruthless eviction policies just to keep the whole factory from overflowing. But before anything actually gets built, it's got to get past the verifier. This is your lightweight QA scanner doing signature, nonce, and basic policy checks. I like to picture the verifier as a massive, unforgiving bouncer checking IDs at the door. It just immediately tosses out invalid inputs before they can sneak in and waste any of the factory's heavy-duty manufacturing energy. And then finally, we reach the big guns, the heavy machinery. The execution engine is our deterministic manufacturing press. It's what actually stamps out the stateful logic. Right next to it is the state store. That's the highly secure warehouse keeping all the resulting persistent account data, program binaries, and Merkle structures locked down and safe. When you put it all together on a spec sheet, it's a beautifully tuned assembly line. Every single component has raw materials going in, finished products coming out, and one critical metric we use to measure its performance. Like, look at the RPC layer. It takes in requests, spits out API responses, and we measure it by P99 request latency. Or the execution engine, taking verified transactions and pumping out state deltas, which we track by execution time per transaction. It's a really elegant setup. All right, Part 3, the transaction factory line, step by step. Now that we know the machines, let's track a single transaction as it rides that assembly line, from the user's initial click all the way to permanent storage. It's a strictly chronological flow. Step 1, intake at the network and RPC layer. Step 2, bouncing the bad actors at the verifier. Step 3, buffering the survivors right there in the mempool. Step 4, deterministic execution. And Step 5, that final atomic commit to the state store. Just a relentless, orderly conveyor belt. Which brings us to Part 4, real-world node roles, and how we actually shift these gears. So here's the secret. Not every factory is built the exact same way. These components map directly to operational choices you make when spinning up a node. Let's compare two big ones. A validator node. That needs heavy-duty execution and robust peer-to-peer networking because it cannot accept eventual consistency. It needs canonical, strict state. But an RPC node, that completely shifts the focus. It emphasizes the RPC and JSON layer and uses a decoupled fast cache state snapshot just to keep user API queries incredibly fast. And what if you're running an indexer? Well, in that case, your factory basically bypasses the execution engine entirely. An indexer relies purely on streaming committed transaction receipts into a read-optimized state store. So you're essentially trading immediate exactness for lightning-fast query speeds. Moving to our final main section, Part 5, spotting the bottlenecks with telemetry and observability. Look, a complex machine is practically impossible to fix if you don't have the right gauges. That's where telemetry hooks into every single layer. The golden rule here, Instrument every handoff. By attaching traces and concise metadata at the exact boundary between any two components, you can follow a transaction from that very first RPC request down to the final state commit. You literally eliminate the guesswork of debugging production delays. So how do we actually decipher those warning lights on the dashboard? Well, if your P99 RPC latency spikes, your traces will tell you immediately if the transaction is stuck at the verifier, churning in the mempool, or lagging in the state store. High mempool churn? Probably an unstable network or bad eviction policies. Unexpected state divergence? That's a classic execution or persistence bug. Good telemetry turns you from a random guesser into a master mechanic. And finally, conclusion and next steps. Let's wrap up the tour. Before we clock out of the factory for the day, let's just quickly distill the core operating principles of the SVM client. Number 1, always treat your components as distinct services with extremely clear inputs and outputs. Number 2, instrument every single handoff for maximum observability. And number 3, configure those component trade-offs based on your node's specific real-world role, whether you're validating, serving RPCs, or indexing. As we finish up here, I want to leave you with a bit of a provocative question. How did these exact same gears shift and assemble differently in an EVM machine? Keep this blueprint handy as we move to our next lesson where we contrast these architectures. And hey, remember to visit forge.college to dive deeper into this explainer and other Web3 topics made by Forge College. Thanks so much for taking the tour with us today.